Good morning or good evening, everyone in your part of the world. My name is Andrea Diambra, and I'm an associate professor of geotechnical engineering, that is a branch of civil engineering. If you don't know what is geotechnics or geotechnical engineering, you may learn something later, because I will concentrate mostly on my subject beyond giving you an overview about civil, aerospace, and mechanical engineering. That in Bristol is all within the same school that we call CAME School of Engineering. You can see CAME is for C for civil, A for aerospace, M for mechanical, and E for engineering. So in the next 40 minutes or so, I'm going to concentrate on three main parts of my presentation. First of all, I'll give you a taster lecture of what is civil in civil aerospace mechanical engineering, concentrating on my interest. But before that, I'll also introduce more generally the subject of civil aerospace and mechanical. Then we'll move towards an overview on what is studying and learning in the CAME School of Engineering. And finally, we spend 5 minutes on the admission criteria. So let's now start with our presentation, the main part, that is the taster lecture. But first of all, what is civil engineering? In civil engineering, we like to use this quote from the Institution of Civil Engineers that say that civil engineers are those people, creative people, that solve problems for the benefit of humankind and our planet. And we like this quote because if you think about your life is shaped the way in which we live, in which we move, in which we can consume energy, is actually shaped by civil engineering, because it's civil engineering building your houses, giving you the chance to travel to airports, roads, tunnels, is bridges, is those that bring you water, because is what civil engineering, they build aqueduct, they build dams to give you clean water, but they will also look after your waste. So actually, civil engineering is shaping our life. And we think that the civil engineer, they design, construct, and lead local, but also large-scale projects. This is something that I would like to make you think about. Think about the structure that you're going to design when you're civil engineering. You're going to design very large structures, huge. So bridges that may be kilometers long, buildings that may be 100 meters high, stadium, very long motorways with a lot of junction. So if you look for a career in civil engineering, you are thinking to build iconic structures, maybe structure that when you will go around, you say, oh, I was part of that project. So that is very, very rewarding. And is also very broad, as you can see from the many examples I gave you here about what it can be a career in civil engineering. And I can praise again the same way aerospace engineering. And maybe you want to become an aerospace if you like to fly, if you like going out in space, if you like to dream in that direction. Because aerospace engineering, especially in Bristol, will teach you how to build aircraft, as you can see here, but also satellite, also drones that are very important for our society in many aspects now, but also about energy. The blades of wind turbine, we'll talk a lot about that later, are designed by aerospace engineering. But also if you like cars, if you like speed, like Formula One, aerodynamics, that is the career in which you want to go. And mechanically, it is not less than the other. It's another very interesting subject. And if you like to build mechanical system, moving parts that will be to support all the other engineering, and this is a thing that I would like to tell you. All engineering are actually very, very interconnected, because as mechanical engineering is supporting aerospace, civil, maths, computer science, and they are supporting each other in many parts. Also, all the branches of engineering are very interconnected. So when you choose one or the other, you will be in a very broad and multidisciplinary topic, actually. So hopefully I gave you an overview about civil, aerospace, and mechanical. Let's now move more about my own interest, as to show you how your career may develop in the future. And what I would like to give you, spend 15-20 minutes maybe in think about engineering for offshore renewable energy. Because if you think now, what is the main challenge faced by our world? It actually is the climate change and the energy crisis. If you look in this chart, I just give you an idea of how our energy consumption, due to the growth in population, the way in which we live, has changed, has peaked in the last 200 years. The energy need is huge now compared to what was a couple of hundred years ago. But this has come too expensive to a lot of pollution and also to impact of our life in the climate. So there's a lot of discussion trying to now change the way we live, change the way in which we use and produce our energy, and our target is actually to get net zero emission by 2050. And this has two implications of us as engineering. First of all, there will be a lot of investment, a lot of money in clean energy sources. So there will be new jobs, economic growth. So this is a sector in which there will be plenty of opportunities for a safe working future. But on the other hand, it's not just this practical and aspect. There is the aspect about passion about your work, because in order to deliver this new energy system, clean energy system, engineer will face quite a lot of challenges, and you will see later the challenges that we are trying to help to give a contribution in my research. And so every day to build new energy sources, or to use new energy sources, you will have new challenges, because you need to go in an uncharted area. But at the end of the day, you will have a lot of reward, because first you have solved these challenges, but also you have contributed to our society towards our target, that is the emission. In this chart, I would like to show you how renewable energy is now increasing, the use of renewable energy in the last 80 years, and how some sources like solar, wind, and water, now they are the main source of energy. And as an engineer, what we need to do, we need to build big dams where we can then use the hydropower to produce electricity. We can use the sun to photovoltaic panels, but also we can use the wind. And this is where I would like to spend my time to tell you what are the challenges. When you talk about wind, you can talk about offshore wind, so out in sea, or onshore. The discipline has started with onshore installation, so inland, but now we have moved out in the sea, where we have much larger and stronger resources. Because what we do, we basically transform the force of the wind to the rotation of the blades into electricity. And these wind turbines are typically installed in farms. This is what we call farms here, and all electricity is brought to the shore through some cables. To give you an idea, 20 of these turbines of 10 megawatt. 10 megawatt is what we install conventionally nowadays, even if we are already talking about 50 megawatt turbines, will cover the electricity of about 500,000 people yearly. So basically, this is a city like Bristol. So you can see how much electricity a single wind turbine can provide us, and how good source of clean energy is this offshore wind. And this has been a very important source of energy that has seen a lot of growth. So if you now want to have an idea about the size of these wind turbines, these are huge. In 1995, 1 megawatt turbine were like, we can say 70-80 meters height. But now what we are thinking to install in just a few years are 50 megawatt turbines that are higher than the Eiffel Tower in Paris. So we are actually height larger than 300 meters. Imagine that this blade only one single blade, maybe just as 100 meter long. So these are huge structure. And we discuss later about the huge challenges that engineers will face to install this out of sea. But this is, despite the challenges, we are actually succeeding in installing this turbine. You can see in this graph what is the cumulative offshore wind capacity that we have installed from 2010 to 2018, where I found this article. But now you can see other data. We are above the 35 gigawatt of installation that were predicted. Most of the installation are indeed in North Sea. These are these areas in which the wind turbine has been installed. But now markets are opening up. We have the initial wind turbine in the east coast of US, but also in the southeast of Asia. I was working last week in a project to collaboration with the company just in the coast of Taiwan, that we face incredible challenges like earthquakes and typhoon. And this is the beauty of engineering. Really, I would like you to show this, because building something in the UK is not the same as building in other parts of the world. And if we think about an offshore wind turbine, we may think about climate challenge, environmental challenge, like wind speed, like earthquake. But if you then project this to other side of engineering, like buildings, then civil engineering becomes a very rich discipline, because you need to know the culture, you need to know how the people live. Make a house in Asia is not the same as in the North Pole, because of climate, because of how people like to live. So whenever you actually go to deal with the project, the first thing you need to do, you need to do some research. You need to know the culture of the people, you need to know the materials available, and that is what makes our discipline very interesting, very diverse, and you will face a new challenge in any new project. But coming back to the wind turbine, this is not just a diverse discipline, but also an interdisciplinary design. Because when you build this wind turbine, you need to interface with the mechanical engineering that are building the rotor, with the aerospace engineering, think about how to make the blades more efficient. Now we have blades that are changing shape depending on the wind. And then the civil engineering will think, but also the aerospace will think about the structure, making sure that it doesn't vibrate too much, that it doesn't go into resonance and collapse. And then another important part is the foundation. That is where is my interest lies, that how you make sure that this turbine is actually nice and fixed in the middle of the sea, when you can have waves of 12-meter high with very high wind speed. And if I tell you how much movement we can allow here, I will tell you that is just a couple of centimeters, because as soon as this turbine goes an inclination larger than 1.5 degrees, then the system is not working. And then we have the mechanical electrical engineer dealing with the cables, but also we need to think about other aspects, that is the wildlife. That is the way in which the seabed sediments are moving. We need to know the waves and the wind forces, so we need meteorocean data from other disciplines. And we need also to think about the social impact. You build this out at sea, so people will see that. So we need to look a lot of aspects that goes beyond engineering. And if you think about the foundation, so my own specialties, here you have several options. And so you can go from a gravity foundation, so just a slab on the soil. We can build a big pile. We can build some caissons that are reverse glasses, so that are just a cup that is for pushing the ground to some suction, or you can have some more complex structure. But what I would like to show you here, just to tell you that monopile is the most used foundation system, is to give you an idea of the size. Because if you think about 40-50 meter water depth, but plus you need other maybe 30-40 meter embedment depth, you are ended up with a structure that is 100 meter diameter length for diameter that can go between 5 and 10 meters. So we are thinking about handling huge structure out in the sea, and think about how you store this in the sea, in the middle of the ocean. So these are the big challenges that we face every day. But I have a dedicated slide later. But before you start with design, the question is, and this is just to give you an overview of what you will learn in our courses, what do we need to know? If you know, the first thing we need to know is the water depth, but also the soil condition. But how do we know the soil condition down in the middle of the ocean? And here is where other disciplines like mechanical engineering is coming to help, and when you need to interface with all other type of engineering. Because with a vessel, we can go out to sea, and then we can have some echo sounders, so some waves that tell us how deep is the water. But these waves can tell also something more, to some geophysical survey about the soil, about the sediment, about how if there are different type of soil and which kind of soil. And then we can use a lot of these we call ROV, so remote operated vehicles that we can just send down in the sea to have some scan sonar or some magnetometer that give us more information. And this is quite interesting. And don't be surprised if you work in this project and you will find an exploding bomb down in the sea. You find a ship relic from 200-300 years ago. So it's very interesting. And so every time we start with this investigation, it's like going down in history, but not just on what's happening on the surface, because then we need also to grab soil sample. And this soil has been created maybe millions of years ago. So you find fossil. You need to know the history of the soil, because depending on how the soil was created, you will have the different properties that will affect your design. So every time we do an investigation, is really is a journey. We like to see it as a journey, and you learn quite a lot of interesting things beyond engineering. So once we know the water depth and the soil, then we need to start the design. And the other thing we need to know is the forces. So you must have people that tell you what is the wind forces and what is the water forces. So again, it's interfacing with different disciplines. And then maybe is where your math and physics will come into play, because once you know all the forces, we can design the foundation, because we know that under these forces, our turbine will incline. So we can know now the pressure that you have to devise to some mathematical expression from your soil knowledge. And then you can do some moment, force and equilibrium, and you can design your foundation that I told you can be very, very, very large, typically very, very large. And this is why the math and physics is important. But engineering is not just math and physics, because once you know that this pile is 100 meters long and is 10 meters diameter, the big question, the most challenging question is, how do you install it? How do you fabricate it? And this is where is coming the engineering. So think about the logistic of this. These are not obviously monopiles, but other type of foundation. Think about the logistic of building these big structures and storing them. So have you got the facility to build it? Have you got the facility to move it? Have you? How do we store it? How do we bring out the sea? So you can see then we need very large vessel like this vessel here. And then once we're out to sea, how do we actually have a base fixed platform, solid platform that we can use? So you can see now we got this vessel with legs. So these legs, they actually can be lowered, they touch in the seabed, and then the vessel comes up when you to offer you a stable platform to work and start the installation. But how do we store if we have a monopile? Then we need to have big hammers. And this is where the mechanical engineering and other discipline will come to our support. And it's not just that; it's also about thinking about costing. So you need to think about the delivery time and think about the installation, because when there is a storm, you cannot install. Because it will be unsafe for the people working in this platform. So we have very short weather windows to install our foundation, typically in the summer. So we must make sure that all these materials, all these foundations are really fabricated in the winter, ready for the summer, and ready for a very short time period. And this is where the engineering is mixing with the physics, with the math, where you can see now you are thinking about an all-rounder discipline. And that's not all, because then we have already future challenges. It is about going in deeper water. And we go to deeper water, then the foundation must be different. And when the water is 200-300 meters, there is no monopile that you can build and you can install. So we're already thinking, actually there are some pilots, as you can see, plant of floating wind turbines. And if you look about the size, I mean, this square area is 40 meter by 40 meters. So the height of this turbine is already in excess of 150 meters. And this is a completely floating wind turbine that is installed in the coast of France. The project is called Ideal, and this is the WindFlow project, another type of wind turbine that is now being installed off the coast of Portugal. So, and this is the future challenges that maybe in 4 or 5 years, when where you be graduated, is one that you can contribute for the installation around the world, and to help to fight this climate crisis. So I hope this gave you an idea of what you will learn in our course. I focus mostly on geotechnical engineering and civil engineering, but if you go in aerospace mechanical, you will have very similar challenges. So to give you an overview of the CAME school, we have obviously 3 departments, that is civil, aerospace mechanical engineering, and in each department you can choose different degree program. So you can choose the bachelor degree program, that is 3 years, or you can do the master engineering program, that is 4 years. It is if you do full-time attendance. There are some variation in the MH, so there is a possibility for you to enroll in the MH, we study abroad in modern language. So you will study a language alongside engineering, and you will spend the 3rd year overseas in, for example, in France, in Spain, or in Germany, where you will be taught in the language that you have learned in year 1 and 2. If not, there is also a possibility to go abroad for 1 year in year 3, but to have that year taught in English. That is MH, we study abroad. Remember that there is a competition, so the place is not guaranteed. Or there is also the possibility to spend 1 year in industry, where you will now do a 5 years study full-time, and in your 3rd year you will have a placement in the industry. You may have understood that these disciplines are very related, and we like to have a very good connection in Bristol between the 3 departments. So when you will join one of our departments, you will have a common first year across the 3 cohorts, with the exception of 1 single unit to date, that is more specific to the subject. And just to let you know, all degrees are accredited by the relevant professional bodies. So I will now spend 5 minutes for each department, roughly. So let's start again with the civil engineering. And maybe what I say here is, I'll highlight it is applicable to all to engineering. So I don't want to repeat many information. So, but I will highlight you which are in common. So all the 3 departments and as civil engineering, they are research-led teaching. So we have our academic, most of them are both lecturer, but also researcher. And for that, across the School of Engineering, we have built some world-class laboratory facilities that I will show you in a second. If you think about civil engineering, you may, as I say, is a very broad discipline. I give you here an idea of the main strand, but also on the type of structure and topic that you will learn. But most of all, I would like to show you some example of how you use our laboratory. And this is an example from the year 2 competition. Maybe it's better if I just show the video, and where the students have learned how to design a building to resist the earthquake. Bristol Civil already suffering, and now the size of the increasing, to other building that was double the phone, now it's it's very fun takeaway from the technical takeaway from the session. But then it's not just about earthquake. We have a lot of laboratories and teaching facility engineering. You have a fluid lab, a structural lab, wind tunnels, soil mechanics, composite robotics. So we have a lot of research area and a lot of robotics across the school. There's also some open laboratory where you can design, build, and test your structure. We have student workshop and hack space. We have library, computers, student lounge, study room. So it's a thriving environment that you will join. And as I said, we have quite a lot of topics. But what I would like to show you in this slide is that we will involve in major project that is near 3 for this all 3 department. You will see we will join a major research project. So you will work alongside leading researcher in the field to do some real research for your first time. In the near form, you will do a design project. So you design a real structure in groups. And you do that in groups because, as you see, engineering is team working. So we need to develop both the hard skills, the engineering, the math, but also the soft skills. So be able to work in group, be able to deliver your ideas, be able to accept other people's ideas, and if they have different opinions, then how to work together with them. Our teaching is very industrial and well connected. We have an industrial zone office that is shared across the 3 departments that will help you to increase your connection with industry. You will be assigned to industrial mentors from the Bristol region that you will see 2 or 3 times per year typically. If it's not for COVID, the industrial mentors will have an involvement in teaching, but also in your research and design project. And also we offer possibility to have some summer internship and, as you said, the year in industry. In terms of content delivery and learning methods, you can expect, this is for all 3 departments, about 20 hours of contact and learning content per week in year 1. And the lecture will come in a variety of formats. So from lecture, example classes, labs, computing, design classes. We have also site visit, field trip, and tutorials. For civil engineering, you may expect a course size of about 65 to 90 students per year group, depends on the years, the number fluctuates, and typically we have 30 to 45% female students. We offer quite a lot of student support across the 3 departments because you will have a personal tutor meeting you almost every week in year 1 and then less as the year progresses. But also there is a student staff liaison committee where you can give us feedback on our teaching, and we will discuss ways to improve your experience and your teaching. Typically, in the most recent NSS say that Bristol had 98% of our student satisfaction, and also was 2nd place in the Guardian Best University 2021. We are very, very proud of our course in civil engineering because our graduates are recognized by the industry for their high quality in research and design project. And it's not uncommon that our graduates actually win quite a lot of awards in nationally and internationally. And you can see some example here on the right-hand side. And for that, our graduates are very highly sought after the degree. 95% find a job within 15 months with good salary very good starting salary in civil engineering that then will quickly increase with the year. So here are some statistics. Let's now jump to aerospace engineering. Aerospace engineering is a very famous department in Bristol, and the very big strength is that it's at the heart of aerospace in UK. Bristol civil aerospace engineering has a lot of contact with local industry, from the Bristol Aeroplane Company that was developed in 1920s. So Bristol has a very long history where the first box type plane was built, and now is the home of many industries like Rolls-Royce, Airbus, Leonardo, and so on. And in Bristol is where part of the Concorde were built, or the A380, A350 in Airbus, and this collaboration is still ongoing, as you can see in this video, where this is Bristol Airbus collaboration on new wings with the different aspect ratio, just that can adapt it even in shape to make the plane more stable. And these are some field trial in the Filton test site. So if you study aerospace in Bristol, you will find again a very vibrant environment. It's still research-led, as we said. There are a lot of strong industrial connection. The industrial liaison office is also operational for aerospace engineering. The student satisfaction is very high. I provide here some statistics. The cohort now is larger than in civil engineering. You may expect to join a year group of about 150, 170 students per year. And again, you will find you have very high opportunities to find a job immediately after you have graduated. Our graduates are very highly sought. To give you an idea about the multidisciplinary, I had this video here about a project that was between the aerospace engineering in Bristol and the science department, where an unmanned aerial vehicles has been deployed in Guatemala to look to have some recognition around these volcanoes for Volcán de Fuego, to understand when it will erupt next time. And to do this project is not just a interface between aerospace and other discipline, but also within aerospace you must get a lot of skills, a lot of different expertise. So you must know about the aerodynamics of these little planes, but the structure, you must know about the control, the flight dynamics, and all this goes in one single piece of equipment. This was a very interesting project, but you can have other example of this project if you go to the YouTube channels of the Bristol Flight Lab. And to give you an overview about the degree, again, like in other discipline, you will have a first 2 years that is about core units, so more mathematical based, and then when you move in year 3 and year 4, you go towards more optional unit, towards specializing, and most of it you will do a lot of very interesting research and design project. I would like just to jump in the design project that you may do in year 4 that are very interesting. You may choose to do a fixed wing aircraft, so a normal aircraft, a rotorcraft, or an helicopters, or a spacecraft. And as you said, Bristol is an industrial hub, and we take advantage of this. So if you will be involved in a normal fixed wing aircraft, you will indeed be collaborating with engineers from Airbus UK, giving you tutorials, lecture, and also a discussion how to design, how to optimize your design. If you go on a rotorcraft, will be engineers from Leonardo helicopters working with you. And if you look at the spacecraft, will be Airbus Defense Space Department. And here are some examples of the activities from posters or some demos of final prototypes. And finally, I would like to spend a little bit time on mechanical engineering, where this is another hugely diverse discipline that is solving real challenges. I would say climate change, but then you can span across different sectors, from robotics, the transport, the energy, but also the healthcare. So you can really help people around the world. That is what engineering is doing. It's actually helping people all over the world. Our students are very highly sought. 95% of mechanical engineering students are in work or further studies 6 months after graduation. They have a very good starting salaries that will increase with the year. And the other important is the industrial connection. So Bristol is home of 785 firms in advanced manufacturing engineering. And again, in mechanical engineering, like in civil, like in aerospace, we would like to make the most of this connection. And you will see people from industry coming to give lecture, helping you in tutorials, and organizing events at University of Bristol. Especially the links are, as I said, are curated by an industrial liaison office, where we'll have industrial mentoring scheme, also mechanical, like in aerospace and civil for first and second year students, and they will offer also opportunities and support for summer internship. As all the other department is research-led with very high level laboratory and state-of-the-art laboratory, as you can see here. The course size now is larger, is 170 to 200 per year group, and the student satisfaction is again very, very high, 93%. And was the mechanical engineering department was classified first in the Guardian links. So this brings me to the final and short part of my presentation, where we'll deal about the admission criteria. So if you look for an engineering career in Bristol, this is the standard offer at A level is A star AA, that must include A star A in any order in maths and physics or chemistry, further maths or computer sciences, if you are looking for aerospace and mechanical engineering. If you look for civil engineering, is again A star A, but the A star A can be maths and a science-related subject. So a little bit more subject, because in engineering we realize that there are other subjects beyond these, like geography, geology, that will be useful for your future career. But the standard offer is A star AA for all three departments, with little difference in the requirement of the units. If you're doing an IB, an International Baccalaureate, the standard offer is 8 points with 18 at higher level, including 7 and 6 in any order at higher level in maths, either analysis and approaches or application interpretation, and a science-related subject. So is one of these two that are the main admission criteria. You must satisfy some English language requirement, that is typically profile E, that is an IELTS 6.5 overall with 6 in all skills. If you go on the website, you can find more information about profile E. And what we look also is about the personal statement. And it's clear to read the personal statement is really a good personal statement. It's really to think about the motivation, the experience, show the aspiration, and if you can also why Bristol. So it must come from yourself. If you are enthused about the career in civil engineering, I'm sure that you will write a very good personal statement just following your feelings. Okay, with this, I'm at the end of my presentation. I hope that was quite an extensive overview of engineering, civil, aerospace, and mechanical engineering in general, and about the Cambridge School of Engineering. So if you now have any question, I will be happy to try to answer them. And thank you very much for your attention.